friends, and welcome to
Science Go!
Today's topic is quantum mechanics. What is quantum mechanics? Quantum mechanics is a branch of mechanics that deals with the mathematical description of the motion and interaction of subatomic particles, incorporating the concepts of quantization of energy, wave-particle duality, uncertainty principle, and the correspondence principle. In simple words, quantum mechanics is the body of scientific laws that describes the wacky behavior of photons, electrons, and other particles that make up the universe. Quantum mechanics is a mathematical framework, rules written in maths for much of modern physics and chemistry. Quantum mechanics helps in sense of the smallest things in the nature like photons, neutrons, and electrons. Complex mathematics is used to study subatomic particles and electromagnetic waves because they act in very strange ways. Quantum is a Latin word that means how much, so a quantum of energy is a specific amount of energy. Quantum mechanics is very important to both physics and chemistry. It also forms the basis of the contemporary understanding of how very large objects such as the stars and galaxies and the cosmological events such as the Big Bang can be analyzed and explained. The physicist Neil Bohr said, "Anyone who is not shocked by quantum theory has not understood it." Which theory supports that quantum mechanics exists? Imagine throwing tennis balls at a wall. Some will bounce off the wall, but some will travel through the slits. If there's another wall behind the first, the tennis balls have traveled through the slits will hit it. If you mark all the spots where a ball has hit the second wall, two stripes of marks, roughly the same shape as the slits, could be seen. This is how it will look. So these are the tennis balls and the wall with two slits. This is the back wall. And here we have two slits. Tennis balls pass through them. And now this is the back wall. Same shape. Slits can be seen over here. Now let's go into the quantum realm. Imagine firing electrons at a wall with two slits, but block one of those slits for the moment. You will find that some of the electrons will pass through the open slit and strike the second wall, just as the tennis balls would. The spots they arrive at form a strip roughly the same shape as the slit. Now open the second slit. You'd expect two rectangular strips on the second wall, as with the table tennis balls. But you can actually see it is very different. The spots where the electrons hit build up to replicate the interference pattern from a wave. So here the electrons strike the wall, forming two wave patterns. Here they behave as a wave. Earlier they were a particle. And here this is the back wall. Strips can be formed, varying from the darkest to the lightest. Why does this occur? Why didn't they form two strips like the tennis balls did? Let's go more deeper. To find out, you might place a detector by the slits to see which slit on the electron passes through. And that's the really weird bit. If you do that, the patterns on the detector screen turn into the particle pattern of two strips, as seen in the first picture below. The interference pattern disappears. Somehow, the very act of looking makes sure that the electrons travel like well-behaved little tennis balls. How is this possible? Here we have two stripes like the tennis balls did. Earlier they were like waves, and we could see many strips over here. How can this be? It's as if they knew that they were being spied on and decided not to be caught in the act of performing weird quantum shenanigans. This is how it would look. What does the experiment tell us? It suggests that what we call particles, such as electrons, somehow combine with characteristics of particles and the characteristics of waves. That's the famous wave-particle duality of quantum mechanics. It also suggests that the act of observing or measuring a quantum system has a profound effect on the system. The question of exactly how that happens constitutes the measurement problem of quantum mechanics. Now, how was quantum mechanics discovered? In 1900, physicist Max Planck presented his quantum theory to the German Physical Society. Planck had sought to discover the reason that radiation from a glowing body changes in color from red to orange and finally to blue as its temperature rises. He found that by making the assumption that energy existed in individual units in the same way that matter does, rather than just as a constant electromagnetic wave, as had been formerly assumed, and was therefore quantifiable, he could find the answer to this question. The existence of these units became the first assumption of quantum theory. He invented the formula E is equal to hv, where E is the energy elements, V is the frequency, and h is the numerical value called Planck's constant. He had been given a theory that energy flows in packets, and these packets are made of photons. This shows the development of quantum theory. So in 1900, Planck made the assumption that energy was made of individual units or quanta. In 1905, Albert Einstein theorized that not just the energy but the radiation itself was quantized in the same manner. In 1924, Louis de Broglie proposed that there is no fundamental difference in the makeup and behavior of energy and matter. On the atomic and subatomic level, either may behave as if made of either particles or waves. This theory became known as the principle of wave-particle duality. Elementary particles of both energy and matter behave depending on the conditions, like either particles or waves. In 1927, Werner Heisenberg proposed that precise simultaneous measurement of two complementary values, such as the position and momentum of a subatomic particle, is impossible. Contrary of the principles of classical physics, their simultaneous measurements is inescapably flawed. The more precisely one value is measured, the more flawed will be the measurements of either value. This theory became known as the uncertainty principle, which prompted Albert Einstein's famous commitment: God does not play dice. What are the uses of quantum mechanics? The entire computer industry is built on quantum mechanics. Modern semiconductor-based electronics rely on the band structure of solid objects. This is fundamentally a quantum phenomenon, depending on the wave nature of electrons, and because we understood that wave nature can be manipulate the electrical properties of silicon. One of the most uses of internet-connected smartphones is to find directions to unfamiliar places. Another application is critically dependent on quantum physics. Smartphone navigation is enabled by global positioning system. This GPS receiver in your phone picks up the signal from multiple clocks and uses the different arrival times from different satellites to determine your distance from each of those satellites. The computer inside the receiver then goes a bit of math to figure out the single point on the surface of the Earth that is that distance from those satellites and locates you within a few meters. Atomic clocks, which are extremely precise, utilize the many principles of quantum theory to measure time. They do this by monitoring the specific radiation frequency needed to make electrons jump between energy levels. Now, there was a theory that Albert Einstein did not agree to, but Niels Bohr did. So here's how Niels Bohr theory won over Albert Einstein's. In the first thought experiment presented by Einstein, he proposed that if the lid were opened on a full box of photons, allowing just one to escape, it could be measured time-wise by simply measuring how long the box will open. He then said it could be simultaneously measured time-wise by measuring the change in the total amount of energy in the box. He said Solid disapproved the Heisenberg principle, which meant quantum mechanics was inconsistent. After some thought, Bohr replied that if Einstein's own theory of relativity were brought into experiment, the apparent inconsistency could be explained away by noting that the measurement took place in a gravitational field. The apparent inconsistency would be explained away by noting that the measurement took place in a gravitational field. Thus, the measurement of time that the lid was open on the box would depend on its position. Einstein was unable to counter Bohr's argument and lost that round. And that's all. Thanks for watching. Remember to like, share, and subscribe.